This meeting is being recorded.
So the next type of addition reaction that we'll take a look at is in section 8.9, and it is called catalytic hydrogenation. So now we're going to be adding H2. So H and H, no water this time around. So it's not a hydration, but a hydrogenation. So across the double bond, we're going to add 2 hydrogens. This requires a metal catalyst. So things like platinum, palladium, nickel, you may see any of these metals used as your metal catalyst. And we will reduce our alkene, right? Our double bond will be reduced to an alkane. And we generally see with this process a very high yield. So 100% yield is noted here. So the stereoselectivity, like we saw with the hydroboration oxidation, is also syn, strictly syn addition. So this is considered, again, a stereospecific process, and we'll only have syn addition. So we see here when we have these 2 chiral centers being formed, right? Both of our products, right, will be on a wedge, or in this case, we'll have both of our products with a dash, right? So we have syn addition of the hydrogen across the double bond. If we were to try this without a catalyst, we can see that the activation energy is very high, and this type of addition will be very slow. So if we look at this graphically, we can see that the pathway has been changed, and the activation energy is much lower with this metal catalyst. So the reasoning behind the syn addition doesn't have to do with steric hindrance as far as it did with the hydroboration oxidation, but the fact that the metal here, this is supposed to be our metal catalyst, these groups of these darker orbs here, these darker spheres, and then our hydrogen, right, this is our diatomic molecule here, is attracted to the metal catalyst, and the molecule would add on the same side as a result, right? They're added to the same face just because of their binding to the metal surface prior to the addition. So we still get syn addition, we still get an alkane at the end. I'm sorry, we didn't get an alkane last time, but now we get an alkane because we're doing our hydrogenation, but it is still syn addition. So what happens when we end up with a meso compound? We can see here that syn addition, right? So both of our sites here, both of our chiral centers added with syn addition would produce only one product, right? We can end up, right, when we have a symmetrical alkene, we will not get this pair of enantiomers. We're going to end up with a meso compound, which, if you recall from Organic 1, we talked about how there can be more than one chiral center present, but in a meso compound, the compound is not considered chiral overall. So the last topic that we'll discuss within catalytic hydrogenation is when we have a Wilkinson's catalyst involved, and that's what we see down here. So there's different terms for our catalysts. So a heterogeneous catalyst, such as our platinum or palladium metal, would not dissolve in the reaction medium. But when we have a homogeneous catalyst, this would dissolve in our solvent or reaction medium, and you can use ligands, right? These kind of groups that are surrounding a metal. So when we have this asymmetric hydrogenation, when we're creating one chiral center, we can result in a mix of enantiomers, right? Except for that one scenario where we would find a meso compound that was formed. So we have 2 scenarios here, both utilizing the Wilkinson's catalyst with this asymmetric hydrogenation. And if we use a chiral catalyst, so one that has either, R or S configuration, it would be possible to synthesize only one enantiomer, right? So R over S or vice versa. When we use one of the ligands, one of these phosphine ligands here, that would be chiral, right? So we can see when we have all the same ligand utilized here, all these phosphine ligands, and then we have a chiral center here. So on this phosphorus, it is creating this chiral center, and therefore we can be stereo selective, right? We can choose which of our products we want to synthesize